So we are slowly reaching to our halfway mark. 16 classes today. So 40, 42 are going to be the total number of lectures. So good. So I hope you all are learning something new which you may not have given so much attention so far.
Yes, sir.
Yes, sir.
Okay, good. Great. So let's start with this. Now we have understood some waveform symmetry conditions, what should be there in any PWM waveform. And now we are trying to see how this different voltages in any system can be realized. Okay. So we are first seeing the square wave operation. So we have the VRO, VYO, VBO pole voltages, and we have generated the line-to-line voltage, something like this. So as expected, it is 30 degrees shifted and the magnitude is also higher. So here it was VDC by 2. Now it is plus VDC. Correct? This is clear to all of you. And we can see this from the phasor diagram also. So VRO, VYO, VBO, these are balanced three phase. Okay. Now the resultant VRY, VYB, VBR, these three also form the balanced three phase. So the simple way to obtain this VRY is VRO minus VYO. Okay. Now what we are trying to get back to the phase voltage from this line to line voltage, right? So what we need to do? We need to do the reverse process and take this vector again, which is VRY minus, I will not write any subscript over here as of now. Instead of just, I will write VR. So another phase voltage it is there. Now what we need to do basically, VRY is there already and VBR is there. So we are taking negative of that, and if you add it vectorially, what you are going to get is basically 3 times of VR. So what we need to do, we need to divide it by 3 to get the actual phase voltage. That's the simple thing, right? So did you try plotting this on the graph, how it is looking?
Yes, sir.
Yes, sir.
Okay. So how does this look? Is it similar to VRO?
No, sir.
No, sir.
No.
That's good observation. So I draw VRO for clarity again, let us say. So this is pi and this is negative half cycle. And this is how the waveform is repeating. Now what you might be getting, those who have done, they will understand this. VRN basically is having a different shape. Let us say if I divide this entire cycle in 60-degree angles. So how basically it looks like, the voltage levels are different. You have starting with plus VDC by 3, and then the next section is 2 VDC by 3. Then you have again VDC by 3, going to minus VDC by 3, then minus 2 VDC by 3, and then coming back to minus VDC by 3, and the cycle continues. Correct? So voltage levels are clearly different. Now we started with square wave, right? We started with square wave, we went to line voltage, VRY, and we have tried to work again the phase voltage. Let me not write any subscript over here. So, and the shape has changed. So what has happened from here to here? We are not doing anything additional, right? For example, if you take sinusoidal waveform, you take VR, VY, VB as simple sinusoidal waveform, and you generate VRY, VYB, VBR, and again try to work back the VR, VY, VB. Will you see any difference in waveform between these two? Will you find any difference? This is simple sinusoidal waveform, say some Vm sin omega t.
No, sir.
And this is 120 degree shifted, another 120 degree shifted. Then you get the line to line voltage and work back the phase voltage. Similarly, what we have done. Will you find any difference in this process? We are only doing reverse computation. See, whatever we have done over here to achieve this, we have done the reverse computation to achieve this. And mathematically, when we have this kind of waveform, it must be same. It cannot be different. Whereas here something different is happening. Okay,
Sir?
another observation. Yes.
Sir, I have a doubt that sir, pole voltage and phase voltages are different or
That's the question why.
yes.
It is different that we know we are seeing this, but why?
Sir, like earlier we considered from the phasor diagram that VRO, VYO and VB was balanced, but they won't be balanced if we add up.
Exactly. This is the point what I'm trying to say over here. See, when you say balance supply, it means that VR plus VY plus VB, this sum is equal to 0. And basically, this is not true for the pole voltages. If you add, say, VRO plus VYO plus VBO, will you get 0? See, here it is positive, here it is negative, here it is positive. So it can never be. There are only two voltage levels. Sukumar, just mute yourself. Yeah. There are only two voltage levels, plus VDC by 2, minus VDC by 2. At the most, one can cancel the other. But still third one will be remaining. So this sum VRO plus VYO plus VBO is not 0. Although it is phase shifted by 120 degree, we say it is balanced. So this extra voltage what you are having over here, this is basically called as the common mode voltage. So if I write over here as VCM, so this is the common mode voltage, and the way to get is like you take average of all three, VRO plus VYO plus VBO divided by 3. This is the common mode voltage, which is superimposing the pole voltage. Okay. This is superimposing this pole voltage apart from the fundamental and all that. We will see what that component is actually. Now, when you have this kind of common mode, which means it is commonly there in all three voltages. So whenever you take line to line voltage, this gets cancelled. So here in this operation, you have cancelled the common mode voltage in the line to line voltage. Now, if you plot the VRY, VYB, VBR, this definitely would be equal to 0. The sum will definitely be 0. Because whatever was common, which was not allowing it to go to 0, that is cancelled. And hence, what you have basically, when you try to work back the phase voltage, you are generating something, let's say this VR voltage, which is actually different from the pole voltage only in terms of the common mode voltage. So simply you can say VR plus VCM is your VRO. So VCM will nothing be but something like, okay, if you let's say draw here, so this is VDC by 3, so VDC by 6 minus VDC by 6, again VDC by 6 minus VDC by 6, again plus VDC by 6 minus VDC by 6. You understand this point? This is the common mode. If you add VRO, VYO, VBO and divide by 3, that is what you are going to get. And these voltage levels are VDC by 6. This is repeating at triple frequency of the fundamental. In one fundamental cycle, there are 3 cycles of this common mode. You see that? So if you simply add these two voltage levels, you will reach here. If you add these two voltage levels, you will reach here. If you add these two, you will reach here. You understand my point?
Yes, sir.
So this component basically consists of all the triplen harmonics. When I say triplen harmonics, it is not just third harmonic, but also the 9th, then 15th, then 21st, and so on. Multiple of 3. And we know that because all the symmetries are maintained even in this waveform. If you take the half cycle, half wave symmetry is there. If you take the quarter cycle, quarter wave symmetry is there. So this is going to have only this third frequency or the odd multiples of this third frequency, which is 3, 9, 15, 21. You understand the point?
Yes, sir.
Correct?
Sir, please repeat. Sir, please repeat, sir.
Manvendra, you first attend yesterday's class.
Okay.
Lot of story is missing. So if you don't see that directly sit in the class, then you will certainly not get.
Okay, sir.
Okay, clear to everyone? Any doubt here? Anybody? Ashish? Drishti? Sampan, Saurav, Shambhunath, Sukumar?
Yes.
Any doubt here?
No, sir.
Good.
No, sir.
So what we are finding that the common mode which is generated in this pole voltage, and we are not doing anything extra to generate this. This is inherently there because of the nature of the waveform. It can have any odd harmonic, right? Including the fundamental. So definitely when odd harmonic is there, first is there, third is there, fifth is there, seventh is there, ninth is there, 11th, 13th, 15th, etc. All are there. So all these triplet harmonic components which are coming, these are basically forming this common mode. For example, if I take just one harmonic, so we have seen that the nth harmonic for the R phase, let us take R phase only for simplicity. The nth harmonic for R phase can be written as 2 VDC by pi times of sine n theta, right? Similarly, for the Y phase, it can be written as 2 VDC by pi. This is nth harmonic. Please note that, okay, let me write in a different manner so it does not confuse anyone. Let me write the n here. This is nth harmonic component I am talking about. So this will be n times of theta minus 120 degree, right? This is the balanced three-phase system we are talking about. Then VBN would be 2 VDC by pi times of sine n theta plus 120 degree. Now, if you plug in, let's say n equal to 1, you find the balanced three-phase voltage, which means VR1 is basically 2 VDC by, okay, n is also here. No? So 2 VDC by pi sine theta. Then Vy1 is basically 2 VDC by pi sine theta minus 120 degree. And Vb1 is basically 2 VDC by pi sine theta plus 120 degree. So this is forming a balanced three-phase system. And also this is positive sequence, what we say, right? So which means that RYB, if you draw, there will be counterclockwise direction of rotation. Understanding my point? Is that clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Now, the same, whatever we have here, you try keeping n equal to 3. So what will happen? This is 3 theta. So VR3 will be 2 VDC by 3 pi sine 3 theta. Then Vy3 will be 2 VDC by 3 pi sine. Now this is 3 times of theta minus 120. So 3 times of 120 is what?
Again, same, sir.
Correct? So this becomes 3 theta again. And similarly, you have VB3 also coming as 2 VDC by 3 pi. Again, 3 times of 120. What is that? 360. It again becomes 3 theta. So these three are basically the same voltages. There is no phase shift between the three. Hence, it is called the common mode. If you draw the three-phase, three-phase component for this third harmonic, it will all be overlapping, RYB. There is no phase shift. Hence, it is called the zero sequence. It is not rotating anywhere. In the phasor, it will just remain stationary. You understand my point?
Yes, sir.
Yes, sir.
This is true if you take any value of n, which is multiple of 3. So m could be 1, 3, 5, 7, etc. If n is this, because even cannot be there, so I am taking only odd numbers. So this is true for all the triplet harmonics, 3, 9, 15, 21, etc. Everything. And that everything combined forms this third harmonic square wave, what we have seen as the common mode. Understanding my point? So now what we have basically, first is forming a balanced three-phase system with positive sequence. Third, 9th, 15th, etc. are forming zero sequence. Now, what is happening with the fifth harmonic? Let us see. So if you try to work out VR5, it will be 2 VDC by 5 pi sine 5 theta. Vy5 will come out to be 2 VDC by 5 pi sine 5 theta plus 120 degree. Just check the values. 5 into 120 is how much?
600.
600. Minus 600 can be written as plus 120, right? Or not?
Yes, sir.
Yes, sir.
If you add 720 and subtract 720 to balance it, what this will form basically? With respect to 720, it will form plus 120 degree phase for the Y. So basically, Y is coming as plus 120. And B, you work it yourself again, when you complete the class. This will form basically 5 theta minus 120 degree. You see this? The sequence has changed. Now here, if you draw the phasor R5, this will be Y5 and V5. So this will be the clockwise direction rotation. So all the fifth harmonic components are basically forming a negative sequence. And still it is balanced. There is no problem in the balance. This is balanced three phase. If you add at any moment, all three will cancel each other. But the sequence is negative. You understand the point?
Yes, sir.
Similarly, if you solve for seventh, the seventh will form basically again a positive sequence. You check it yourself. 7 theta, Vy7 will be 2 VDC by 7 pi times of sine 7 theta minus 120 degree, and Vb7 2 VDC by 7 pi sine 7 theta plus 120. This will again come back to the positive sequence. And this has very important role, how it generates the torque, how it generates the other things. No, this has very important role in that. This is also balanced three phase. Similarly, you keep going. 11th will again form a negative sequence. 13th will again form a positive sequence. So alternatively, these will keep changing. These harmonics will keep changing their sequence of rotation. Okay, you can check. So this has impact on how flux is generated in motor and all. So we will see that in coming lectures. Now this is what we have understood. Okay, about the harmonics, the nature you have understood, right? Yes or no?
Yes, sir.
Yes, sir.
Now, one important thing when we are referring to this phase voltage, what this voltage actually is, how to name this, like VRO is basically voltage at point R with respect to O, the midpoint of the DC bus voltage. Here actually when you have worked back the phase voltage from the line to line voltage, this is O and you have RYB terminals over here. Say this is the RL load what you are having. Okay, for simplicity. Balanced three phase RL load. The neutral point of this is generally not connected to the midpoint of the DC bus. Generally, otherwise we will have path for some other currents which are unnecessary. Unless it is very much needed, it should not be connected. So when we say the VRO, we are referring to the term called as pole voltage. When we are referring to VRY, we call it line to line voltage. Okay, just understand these terms properly. And when we say that phase voltage which we have worked out through the line to line voltage, this we basically call as VRN or VYN, VBN. Now we are taking with respect to this neutral point. So these are called line to neutral voltage. You understood the difference? In any system, if you measure the voltage between R and O, you will have a different shape. But if you measure between R and N, you will have a different shape. And the reason lies here, how it is getting derived. So the different names are there. All this VRO, VYO, VBO, we always refer to this as pole voltage. Whatever is coming between the two phases, that is line to line voltage. And then whatever comes after the line to line voltage computation and back to phase voltage, that is referred to as line to neutral voltage. Basically measurement with respect to this neutral point N. It need not be grounded. Okay. This need not be grounded. We are talking about 3-wire system. There is no unnecessary grounding or connection anywhere. Understanding my point?
Yes, sir.
Good. Now, once you have understood this, now let us see little bit more about these harmonics, how its magnitude is coming into any system, and then what is the impact of that magnitude on the system. So let us see that we have, say, first simple thing what we have taken is square wave. So, okay, one more important term which I have missed out. So we sometimes refer to this voltage, what we are generating as this, this line to neutral voltage, VRN. Sometimes we refer to this as 6-step voltage. 6-step because there are 6 steps, 1, 2, 3, and then this 4, 5, and 6. So 3 on the positive side, 3 on the negative side, we call it 6-step voltage. So whenever you hear the term square wave operation or 6-step operation, these are all same. Understanding my point? For two-level volt, this VSI, these terms are basically referring to the same mode of operation, whether it is square wave mode of operation or six-step mode of operation. This is basically same thing, just called differently. Fine. Now,
Yes, sir.
let us go to the square wave again and let us see how the harmonics are placed. So because now we have balanced three-phase system, analyzing only R phase is sufficient to know about all the system, and within R phase only a quarter cycle is enough because all the symmetries are maintained. So this point is clear. Then we have, let us say Vn, the nth harmonic can be given as, and particularly the magnitude I am talking about here. I am talking about the magnitude of this nth harmonic. This is true for all, right? R by B. And we know very clearly that 1, 3, 5, 7, 9, 11, 13, 15, these are present in the pole voltage. But in the line to neutral voltage, we will be missing these harmonics, all the triplet. That's the only difference between pole voltage and neutral voltage, line to neutral voltage. So if you are asked that, let us say, do the Fourier analysis of line to neutral voltage and get the component of harmonics present over there, you need not do the computation for this. This may be difficult. It has different shapes coming different places. Simpler thing could be that you do the analysis for a square wave and just forget these points, these harmonics in this waveform, and then it is this. These two waveforms are different only in terms of triplet harmonic. Rest all things are exactly same. Exactly same fundamental value, exactly same fifth harmonic, seventh harmonic, 11th, 13th, and so on. You understand the point? So basically this plus the triplet is equal to this. There is no other difference. So for simplicity, we always do Fourier analysis of pole voltage because it's having only two levels, which is easier to analyze. And then once we get this, we know that only we need to forget about the 3rd, 9th, and 15th and so on. And then the same thing is true for the line to neutral voltage. So considering this here, now we are trying to see how the magnitudes of different harmonics are placed in the system. So system, when you have three-phase, three-wire system, you will not see any triplet harmonic flowing into the system because it is cancelled in the line-to-line voltage. So we need not worry about this. This is also gone. We have removed the even harmonics by keeping the symmetry, and we have removed all the triplet harmonics by keeping three-phase symmetry. So only we need to worry about harmonics which are like fundamental, 5th, 7th, 11th, 13th. And apart from fundamental, these 5th, 7th, 11th, 13th, then 17th, 19th, etc. These are the harmonics which we need to worry about. Is my statement clear to all of you?
Yes, sir.
Yes, sir.
This is what we need to worry about. Deepak, are you there? By any chance, Deepak? Okay. That's not the way. That's why I asked all of you to turn on your camera, because this is what happens. You simply be in the meeting and then you go somewhere for shopping or something. No, you don't know for what purpose. Okay. Now, let us try to see what is happening here with the harmonics. So the magnitude, if you notice, is basically divided by n, right? Where n is the harmonic order. So if you try to plot the magnitudes of different harmonics with respect to the harmonic order n, what we will find that maximum magnitude is seen for the fundamental. Okay, so we have say first here, and then third may be missing, so we need not draw. Then we will have fifth, we will have seventh, then again ninth will be missing, then we will have 11th, then we will have 13th, then we will have 15th is missing, so we have 17th, then we have 19th, and every harmonic is basically divided by this harmonic number n. So starting from here, if this is 2 VDC by pi, for 5 you will see 2 VDC by 5 pi. For 7 you will see 2 VDC by 7 pi. For 11 it will be 2 VDC by 11 pi. So basically the harmonic magnitude is reducing with the harmonic number. That is how these harmonics are placed in terms of magnitude in the waveform. Okay, I should have drawn it from here, not the DC component. It should start from here basically. And it will keep going up to a very high order of harmonic until the magnitude becomes insignificant. So this is how these are located. Now we have seen that when we are having a square wave mode of operation, the magnitude of fundamental is fixed. We cannot do anything about it, right? So to have some control over the fundamental, we had introduced one switching angle in the quarter cycle. Now, what we have done basically, we have introduced one switching angle and we are maintaining all the symmetries in the waveform. That means if this is alpha, we know that all other angles are placed appropriately. This is pi minus alpha, and then we have the negative half cycle with all the angles. So this is continuing, and the three-phase system is also balanced. So we only need to analyze 1/4 of the VRO, 1/4 cycle of VRO, and we can understand the properties of the complete three-phase waveform. So what we have found that VRO is basically any nth harmonic in this system can be written as isn't it? This is what we have derived. If you keep all the symmetries in this, then this is what you are going to get as nth harmonic. Now we have a control parameter, say alpha, which means what? If you talk about V1, then the magnitude is basically dependent on at which angle you are operating. It is not just the DC bus voltage, but this angle is also dictating that what is the magnitude of your fundamental. So if we try to plot this with respect to alpha to just understand how it is varying with respect to alpha, and we have to keep sure that V1 magnitude is greater than 0. No, we only operate with positive voltage. We should not suddenly invert the voltage, go to negative value. That is not recommended. So what we have basically, if you plug in alpha equals to pi by 3, what will happen? If you plug in alpha equal to pi by 3,
Zero, sir. Zero.
V1 will be 0. And if you plug in alpha equal to pi by 2, then
Maximum, sir. Maximum.
is 2 VDC by pi.
3/2.
Correct? So what is happening that if you change your angle from pi by 3 to pi by 2, the magnitude is increasing in this manner. Now, can we have alpha greater than pi by 2?
No, sir. We are talking about only 1/4 cycle.
Correct? No, it's not just talking about 1/4 cycle. Physically also, it is not possible to have a switching angle more than 90° and then maintain all the symmetry. You cannot have this pi minus alpha less than alpha physically. Is this possible?
Sir.
Is this possible that you can have pi minus alpha less than alpha? Physically, it's not possible, right? You cannot switch at, no, first say 110° and then at 70°. Can this happen?
No, sir.
Correct. So physically, this is not possible. Practically, this is not possible. So we have limitation for alpha up to only pi by 2. Now, if you go less than pi by 3, what will happen? V1 will start going negative. Just check value for alpha equal to pi by 3. Sorry, pi by 6, not pi by 3. For 30°, just check the value. How much value you will get here?
Negative.
This will come as 1 minus root 3, which is basically less than 0. So we don't operate for negative voltage, right? We are only operating for the positive voltage. So our range of operation for alpha is only this, from pi by 3 to pi by 2. It cannot be less than pi by 3, it cannot be more than pi by 2 for these reasons. So this is our range of operation for alpha. Now within this range, we will see how other harmonics are playing out. That also we need to know, right? So for example, if we talk about say V5 as 2 VDC by 5 pi times of 1 minus 2 cos 5 alpha. Fundamental is clear here, right? This is your V1, which is varying from 0 to 2 VDC by pi, and the value is going from 0 to, sorry, the angle is changing from pi by 3 to pi by 2, and correspondingly the value is changing from 0 to 2 VDC by pi, from the minimum value to maximum value. This is what you are operating. Correct? So within this range, how is V5 coming out? Okay, let's answer simple questions. What is the value of V5 at pi by 3?
Zero.
Zero, sir.
Zero. What is the value of V5 at pi by 2?
Maximum, sir.
Maximum.
Maximum.
Maximum, sir.
Pi by 2, what is the value?
2 VDC by 5.
Yes.
VDC by 5 pi.
So at least these two extreme values we know. Now we have to work out between the whatever other numbers are there. So let us say, for example, at what all points this could be 0. So whenever you have 1 minus 2 cos 5 alpha going to 0, V5 will be 0. Which means that your 5 alpha should be something like no multiple of 60°. Not multiple of, but let's say 5 alpha will turn out to be 60°. So if this is true for 60°, this is also true for 300° and 420°. So you add and subtract from 3 and 360 and your result will remain same, isn't it? You understand the point? So this 300, when you take 5 alpha equal to 300, this is what you have computed as 60 degree or pi by 3. And when you take this other option, alpha equal to 420 degree by 5, this is 72 degree. This is the other angle at which your V5 is going to 0. So we have another value at which it is going to 0. Say this is 60, 90, so middle could be 75, and somewhere just before the 60, 90, yeah. So 75 could be here. So something like here, let us say. Similarly, any other angle at which it is going 0? Okay, I think, is there any mistake in this one? Yeah, this is 84 degree. Sorry. Yeah, that's not 72. Okay. Yes. So 84 comes something like 75, and then this is another 15. So 9, let's say somewhere here. At this point, it is going to 0. Correct? So now if you try to work out at what value this is going to maximize, at what angle. So basically you have to find out the angle at which this function is maximizing. 2 cos 5 alpha. Can you figure out the angle at which it is maximizing? Quickly. And what is the maximum value?
Sir, 36.
36 degree.
36.
36.
And 36 is below 60. We are not operating at that. The next number?
36 into
108 degree. Oh, that is
108 is above 90. There is something in between. So by mistake, I told the other number earlier. It is actually 72 degree, right? Yes or no?
Yes, sir.
And what is the value at that point? What is the value at that point?
Sir, at
Sir,
72
BTC
it will
by-
come negative, sir.
Hmm?
It will come negative at 72.
Okay, I am asking magnitude.
Negative.
Minus 2 EDC by 5.
Magnitude I am asking, right? See, whether it is in phase, positive phase or negative phase, that doesn't matter for harmonic, right? So basically what I'm trying to say, that when you try to work out the magnitude, this is going all the way up to 4 VDC by 5 pi, then coming down to 0, and then this. This is how your fifth harmonic is varying in magnitude. Sign may be there, but we are not worried about the sign of the harmonic. We are worried about the magnitude of the harmonic. For V1, we are worried about the magnitude, phase, sign, everything. You understand the point? So basically V5 is coming all the way up to this 4 VDC by 5 pi, and then it's repeating and going back to 2 VDC by 5 pi. When you operate from, let's say, pi by 3 to pi by 2, you will find V1 going from 0 to 2 VDC by pi without any problem. But you will also find that with that, the fifth harmonic is increasing. It will maximize, then it will come down, and it will again go to 0, come back to some value, 2 VDC by pi. Which means what? With this, you have no control over the harmonic. It is doing what it has to do. It is what it is. We cannot have any control, right? When we are changing our alpha, that's the only parameter we have. Understanding my point?
Yes, sir.
Clear? Similarly, you can also work out how V7 is varying. So like fundamental was hardly varying once in this, this 30-degree span. Fifth harmonic is changing almost, let's say, half cycle or little bit more. Seventh will have little bit more variation within this. So like that, the frequency increases. The occurrence of this 0 point increases for the harmonic as you go for higher order. Correct? But the important point to notice over here is that when we have only one variable in our system, alpha, we have freedom to only operate at a particular voltage. We are not able to say or control anything about the harmonic voltage. You understand my point? So what we need basically, we need little bit more freedom in our voltage equation so that we can at least control some harmonics, not everything, at least some harmonics. You understand my point? So what I do basically, instead of having one switching angle in one quarter, I will introduce, for simplicity, this is the bare minimum thing what we can do. I will introduce one more switching angle in the quarter cycle. Say alpha 1 and alpha 2. Of course, these levels are same. You understand my point? Now I have 2 degrees of freedom in my pole voltage. So apart from maintaining fundamental voltage, I should also be able to control any one harmonic or maybe something better. You understand my point?
Yes.
Yes, sir.
So this is our next waveform which can be used practically also for running any system. We have at least some more degree of freedom which is not just giving me a fixed voltage but also giving me some control over the harmonics. Now for the next class what I want, before you come, do the harmonic analysis of or Fourier analysis of this waveform. And then we will see how we can have control over the fundamental, which harmonics to minimize, or can we do something better than having just one harmonic? And then can we have anything about the torque, what is going to come in the system? Because we are dealing with motor drives. So these questions we will try to answer in the next class. Okay?
Yes, sir.
Any doubts, any questions up to this point?
Sir, the peak at 72 degree, it will come as 2 VDC by 5 pi, sir.
Which one? Just a second. Yeah. How much it will come?
2 VDC by 5 pi.
Is it? And 90
Sir,
degree?
at 90 it will be 0.
Which one you are saying?
For V5, sir.
How come 90 is coming 0?
Oh, sorry, sir. For 90, like it will. For 90, it will come 2 VDC by 5 pi only, I think.
Okay.
Indeed
Yeah.
is 2 VDC
This,
per 5.
yeah, this may happen. Yeah, correct. The value of this thing is actually going to -1. So we have actually repetition of this only. I thought this sum is going to 2. So basically we have same magnitude, but it is basically opposite polarity only, right? So actually if you plot it is something like this. But when we are talking about magnitude, it will be like this, the rectified form. This is correct. This is fine, right? The blue waveform is actual magnitude variation. If we take the, no, just the mod of that, it is like this. Correct?
Yes, sir.
Yes, sir.
12, 12 and then 6. Yeah. Okay. Hmm. Okay, I will check this thing once again in the next class. Fine. So let's continue in the next class. Any more doubts in this one? Any more
Sir,
doubts? Hmm.
not in this, but assignment